All right, so video 10, we want to talk about analog inputs and outputs. So I want to talk about configuration of analog I/O and the RS with using RSLogix Micro Starter Lite, and how to go about scaling analog signals for real-world applications. Configuring analog I/O, but your MicroLogix 1000 models that have analog I/O, they have built-in analog input and or output channels, depending on the model. These channels will handle either 0 to 10 volt DC or current signals, 4 to 20 milliamp signals, and to properly configure and scale these analog values in RSLogix MicroStarter Lite, you want to follow these steps. So say for configuring analog inputs, you need to identify the analog input channels. The MicroLogix 1000 models that have analog I/O, not all of them do, but it includes the 1761 L16BWA, the BBB, there's also the L20BWA, etc. Analog inputs are referenced as I colon 0.4 and I colon 0.5 in the data table. The first analog input would have to be the dot 4, the second would be dot 5. So kind of similar looking to digital inputs, but not quite. You've got the dot, the decimal point there representing which channel. um, Analog inputs, to set those up, you'd open up the RSLogix Micro Starter Lite, go into your I/O configuration section under the controller menu, and then you want to check if your MicroLogix model supports analog inputs. The one that I'm working with doesn't support analog inputs, but um, the analog inputs, they're automatically assigned to I colon 0, 4, and 5. So you've got two of them available, and really no other setups required since they're fixed 10-bit resolution inputs. So here's an example of the opening up the I/O configuration for a particular model. You've got some choices in here. You've actually got a listing of hardware that's available that you can select. I'm just, in this example here on the left, I've just got a Bulletin 1763, should be a MicroLogix 1100 Series A. As far as reading raw analog values, the MicroLogix 1000 provides some raw values, either 0 to 10 volt, 4 to 20 milliamp signals. These signals are converted into a raw value from 0 to 1023, which represents 10-bit resolution. So what that means is that if the signal reads 0 volts, your raw value in the PLC is 0 if you have a voltage input, and at 10 volts it would read 1023. Now, if you're using a 4 to 20 milliamp type sensor, at 4 milliamps, you're going to read about 163 as a raw value, and at 20 milliamps, you're going to read 1023. Now, I actually prefer the 4 to 20 milliamps over 0 to 10 volts, and the reason for that is if you have a broken wire with your 4 to 20 milliamp signal, you're not going to have 4 milliamps at the input. So if you're reading pressure, say from 0 to 100 psi with a sensor, you should be seeing at 0 psi, the PLC should have a value of around 163 because you should be getting 4 milliamps when the pressure is 0. If you have anything less than that, it's going to really indicate that you've got a broken wire because you're not even getting, if you get 0 milliamps instead of 4 milliamps, at that input, that's indicating there's something wrong in your analog input circuit. As far as configuring analog outputs, you identify those channels. There's some models that have analog outputs. They're going to be referenced as O colon 0.4 and 5, your first and second analog output. Um, they're also automatically configured with an RSLogix, and the values here, again, this is 10-bit resolution, so your raw output values are going to range from 0 to 1023. Again, at 0 volts, you'll have 0, at 10 volts, 1023 if it's a voltage output. One thing here to keep in mind, scaling analog signals, you got to give this a little bit of thought. If you're familiar with the equation of a line, the y equals mx plus b, the slope and the intercept and so on, um, you got to remember that with this PLC, since your raw analog values inside of the PLC are 0 to 1023, you need to have scaling to match the real world units, which are also known as engineering units. Those real world units could be things like temperature, pressure, and speed, where you've got maybe degrees Fahrenheit, Celsius, PSI for pressure, maybe miles per hour, kilometers per second, whatever for speed. And a scaling formula in order to convert the raw data to engineering units, your scaled value is going to be equal to the raw input minus the raw minimum. So the raw input would be whatever that value is you're reading at your input. Say if we're looking at an analog input, it's going to be somewhere in the range of 0 to 1023. So whatever that value is, you want to subtract the raw minimum. Now, in our case, the raw minimum would be 0 because the range is 0 to 1023. Let's turn this back on. So the raw minimum is 0. The raw input's whatever the input reads. Then the raw max minus the raw min. Well, the raw max is 1023. The raw min is 0. And then you multiply that by your engineering max. Now, if we're dealing, say, in a pressure, maybe I have a pressure sensor that reads 0 to 300 psi. All right, so my engineering max would be 300 psi. The engineering minimum is 0. And then, well, they're just showing adding the engineering min again. But um, remember, the raw minimum is 0 because it's 0 at 0 volts or 4 milliamps. The raw maximum is 1023 at either 10 volts or 20 milliamps. And again, this voltage or milliamp depends on what kind of analog input you've configured. Is it a voltage input or is it a current input? And then the engineering min max was your engineering unit range. For example, it could be 0 to 100 degrees Celsius for a temperature sensor. There's an instruction inside of the PLC. It's called Scale with Parameters, SCP. Now, the MicroLogix 1000 does not have an SCP instruction, so you have to manually scale using math operations. So you got to do some mathematics here to get that to work. So example here, if you want to scale a 0 to 10 volt sensor between 100 and 0 to 100 degrees Celsius, and we're going to say we're going to read I colon 0.4. So we're going to read this analog input. So the formula for that basically would be the whatever that raw analog input value is divided by 1023 multiplied by 100, right? That would be what we would end up with. And here's an example, basically of how you could go about doing it. You move the raw analog input. In this case, we're going to move it into N7 colon 0. We're just moving it to an internal address. Then we want to multiply the raw value by 100. So we're using a multiply instruction here. N7 colon 0 multiplied by 100. And we're going to put that result in N7 colon 1. And then finally, in the third rung, we're going to divide the result there, N7 colon 1, by 1023, and we're going to end up with a result in N7 colon 2. So the N7 colon 2, that integer file, will contain our scaled value between 0, and 100 degrees C. So if we have a value of 50 in there, it's going to represent 50 degrees Celsius. So hopefully that example is helpful. And here's another example where basically we're taking scaling a 4 to 20 milliamp pressure sensor that has an engineering range of 0 to 500 psi. The raw minimum here for 4 milliamps is 163. And the raw maximum for 20 milliamps is 1023. Remember that raw range. Our engineering minimum is 0 psi. Engineering max value is 500 psi. So applying that formula that we had, we've got the analog input minus our raw minimum, and that's divided by our raw maximum minus the raw minimum. And then we're multiplying here by our engineering unit max, which is 500, minus the engineering unit min, and then we're just adding the engineering min again here, which is again is 0, so not really going to change anything. And that would be how you would go about doing that through math instructions. Well, this is the mathematical equation for doing it, but then to actually implement that would be, here's some code that would do that for you. Um, you want to move the, we're basically here going to subtract the offset. This is where we're taking, if you look back here, where we're taking the analog input minus 163, this top part of this division here, this is what's happening right here. We're taking I colon 0, we're taking the analog input, subtracting 163, putting the result in N7 colon 0. And then this is multiplying by 500, taking that value, multiplying it by 500, putting it in N7 colon 1. So basically what we're doing here is we're actually doing this, and then we're multiplying by 500, because 500 minus 0 plus 0 is still 500. So we're doing this in the first rung, we're handling this part, the multiplication in the second rung, and then we're going to do the division in our third rung. We're going to divide by 1023 minus 163. So 1023 minus 163 is equal to 860, right? So we're taking the result of that multiplication, which is an N7 colon 1, and then we're dividing it by 860, and then putting the result into N7 colon 2. So it would be nice if we had the scale with parameters instruction to do all this for us a little bit easier. But you know, it just takes 3 rungs, and we basically have it anyway, just a subtract, multiply, and a divide. All right, now output scaling for actuators is pretty similar here. Say here's an example. Say you're controlling an analog output for a variable speed drive. So you just basically reverse the formula, and your output value is going to be equal to the end, and this time it's going to be the engineering value minus the engineering minimum value, all divided by the engineering max minus the engineering min, and then you're multiplying here by your raw max minus the raw min plus the raw min again. So, you know, an example we've got here, you might have an actuator that requires 0 to 10 volts output to control a motor between, 0 to 100% speed through a drive. So here, we're going to multiply the speed percentage by 1023. So we go back here. I got 1023. We're going to just say that N7 colon 0 multiplied by 1023. We'll put it in N7 colon 1. So N7 colon 0 could basically be our engineering value minus the engineering min, whatever that was. We were actually lacking the subtraction in here. I did not include that. I really should have had a subtraction before this, and the result of that subtraction would have gone into N7 colon 0. And then we convert to the analog output range. We take the result of that multiplication, and then we're dividing by 100. And why are we dividing by 100? Well, we're dividing by 100 because our engineering max and min, it's 100% speed. The engineering min is 0%. So it's 100 minus 0 or 100. So that's where this is coming from. And then our value is output to O colon 1.0. And so if we output a 50 to that, that's going to represent 50% speed. Well, actually, excuse me on that. That's actually going to be the raw value, and not. It's going to be 50% of the raw range. Well, the raw range is 0 to 1023, so you're talking something over 500 is going to be actually output in the output. Because remember, this is an analog output, not, we're not scaling the input to an engineering value. We're going in reverse. We're going from the engineering value to the raw value for the output. So some best practices here to follow. Use integer files, the N7s, for any intermediate values. Since the MicroLogix 1000 lacks any floating pointing math, you may have to go ahead and perform calculations with integers and then just scale them appropriately. Some models have floating point. You get into the processors like the SLIC 500 series, you get into the floating point, but the MicroLogix has some features that are lacking, so you don't get everything with that. And you want to ensure that your 4 to 20 milliamp sensors are wired correctly. And some sensors need to have external power, such, it's 24 volts DC. You may need to also filter out some noisy signals where you can use some move averaging or some logic, to stabilize readings. So again, you want to configure your analog inputs and outputs using the fixed addresses, which are like either the I's or the O's for analog ins or outs. And remember to scale your raw values from 0 to 1023 over to engineering units using math instructions, and then implement your manual scaling using multiply, divide, and subtract. Those are going to be your three math functions that you're going to need to do that. And then when you reverse the scaling formula, you need to reverse that scaling formula to convert engineering units back out to the raw analog output values when you're dealing with analog outputs. All right, I wanted to go back and review this output scaling for actuators example that I have here, and I wanted to actually work it out in the PLC. I think it'll make a lot more sense if I do that. Basically, the formula here is the output value. This will be the raw output value is the engineering value minus the engineering min, all divided by the engineering max minus the engineering min times 1023 minus 0 plus 0, which ends up being just multiplying by 1023 on the right. But we look at an actuator that requires 0 to 10 volts. Output to control is 0 to 100% speed. Now, the scaling, the raw scaling, is 0 to 1023. All right, so we've got that taken care of here. This is the raw value, the raw max minus the raw min plus the raw min. The output value, when I talk about engineering value, that's going to be in percent. So for the example that we're going to do, let's say we want to run this motor at 7%, this analog actuator. We want to run it at 7%. We can run it between 0 and 100%, but we want to run it at 7%. So the engineering value we're shooting for is 7%. Well, what's the engineering minimum? Well, the engineering units is percent in this case. So the engineering minimum is 0 because we can go from 0 to 100. What's the engineering max? That should be 100% minus the engineering min of 0. It might make a little more sense if I show this here. Again, we're going to show it again. The engineering value what we're going for is 7%. So 7 minus the engineering min of 0. And then we're dividing by this denominator, which is our engineering max of 100% minus the engineering min of 0%. And then we're just multiplying here by our 1023. If we work this all out, we're going to get a number 71.61. This is the raw value that we would send to our analog output. This raw value is within the range of 0 to 1023. If we were running this output at 100%, we would be outputting 1023. If we were going to run at 0%, we would be outputting 0. So that means our code, go jump to that window here real quick. We've got a running program here already set up. This N7:10 is our engineering value of 7%. N7:2, we've got that defined as our engineering min. This is 0%. We're doing a subtract. 7 minus 0, of course, is 7. So we're using some variables in here to do this. Then we're taking the engineering max minus the engineering min. 100 minus 0, of course, is just 100. Now note that we're using a floating point here. I'm trying to go for a little bit more accurate result, especially when we're doing our division, right? So 100 minus 0 is 100. Now we're going to do our division. This is basically the numerator from our slideshow here. Let me go back to that. That would be this 7. And then we're going to go back to the code. 7 divided by 100 is 0.07, right? So now this is the result. So if we divide that numerator by the denominator of that equation that we had for the output value, we get 0.07. Then we're multiplying by 1023 and getting 72. So O:1.0 would be our analog output, and we're outputting a 72. Now there's a little bit of some rounding error in here, but 72 is very close to 71.61. So if you'd like to, you might want to work through this example and take a look at it. Take a look at the instructions and how that output instruction works, and hopefully this will help explain it a little bit better.